Welcome to the Explainer. You ever wonder how physicists can predict the exact path of a rocket or figure out the stopping distance of a car down to the inch? Well, it's not magic. It's actually a set of really powerful, surprisingly simple rules about motion. So today, we're going to crack open that very toolbox and look at the physics that runs everything from a sprinting cheetah to a top-fueled dragster.
So, let's kick things off with a pretty specific question. You've got a dragster, basically a rocket on wheels, and it just explodes off the starting line. After just 5.56 seconds, how far has it actually gone? Now, it might feel like you'd just be guessing, right? But as we're about to find out, the answer is incredibly precise.
And here's the cool part. The answer to that dragster problem and so many others is totally predictable. We just need the right tools to read the situation. What we're going to do is build ourselves a physicist's toolbox, a set of powerful equations that'll let us describe and predict motion with, honestly, stunning accuracy.
Okay, but before we start messing with all these problems, every good workshop needs some ground rules. And for us, it really all comes down to one big idea. One simple assumption that makes all this magic happen.
And that big rule is, we're going to assume that acceleration is constant. That just means an object's velocity changes at a nice, steady, consistent rate. No sudden jerks, no lurching forward, like the steady pull of gravity on an apple falling from a tree, or the smooth, constant braking of a train pulling into a station.
Now, I know what you might be thinking. Isn't that just cheating a little bit? The real world is messy, but it's actually a super smart shortcut. For one, it's true for a ton of real-world situations. And even when things get more complicated, we can often just chop up the motion into little pieces, where each piece has its own constant acceleration. All right, so we've got our main rule down. Now it's time to actually open up that toolbox. We're going to pull out three key tools, three equations of motion, that can solve pretty much any problem we throw at them, as long as that acceleration is constant.
First up, we've got what I like to call the speed predictor. It's a really simple, clean little equation that lets us find an object's final velocity, or v, at any moment in time.
Yeah, it's super straightforward. If you know how fast you started, how much you're speeding up, and for how long, bam, this tool tells you your exact final speed. Simple, right? But incredibly powerful. Okay, tool number 2 is the position finder. Now this one is the real workhorse. This is for when you need to know not just how fast something's going, but exactly where it's going to end up.
See that t squared in there? That little piece is everything. It tells us that when an object accelerates, the distance it covers actually grows exponentially with time. That's why something that's accelerating, like our dragster, covers way more ground in its second than it did in its first. The distance doesn't just add up, it compounds.
And for our last tool, we have a really special one. I call this one the timeless equation. The magic here is that it connects your speed, your acceleration, and your distance, all without ever needing to know how much time has passed. It's the perfect tool for when the clock just isn't part of the question.
Okay, so we've got the rules of the road and we've unboxed our three main tools. Now for the really fun part. Let's actually put them to work and see what they can do on some real problems.
So let's go back to that starting line, back to our dragster. We know how long it's accelerating, and we know its acceleration rate. We need to find the distance. Looking at our new toolbox, which tool do you think we should grab?
All right, let's lay out what we know. Well, its starting speed is 0, because it starts from rest. We have its acceleration, and we have the time. The one thing we need to find is its final position, x. So, which tool uses all that stuff to find where it ends up? Yep, it's got to be our position finder.
So we just plug in the numbers, let the math do its thing, and we get 402 meters. And get this. This is the amazing part. 402 meters is almost exactly a quarter mile, which is the standard length of a drag racing strip. The physics predicted reality perfectly.
Okay, let's try another one. This time, it's something we've all felt, hitting the brakes in a car. So a car is cruising along, and then the driver has to slam on the brakes. We're going to use our tools to see how just one thing, is the road wet or dry, can totally change the outcome.
Okay, so for this problem, we don't actually care how long it takes to stop. We know the starting speed, we know the final speed is 0, and we know the acceleration, or deceleration, from the brakes. This is the perfect job for our timeless equation. On dry pavement, the car stops in about 64 meters. But now look what happens when the road is wet. The braking is less effective, and the stopping distance just balloons to 90 meters. I mean, that's a huge difference, and it's a life-or-death lesson written right there in the physics.
All right, for our last problem, let's really level up. We're going to take on a classic physics puzzle, a two-body pursuit problem. Sounds complicated, right? But check this out. We can solve it with the exact same tools we already have.
So here's the setup. You've got a cheetah starting from a total standstill who starts accelerating to chase down a gazelle that's already cruising past at a nice constant speed. We have two different objects with two completely different kinds of motion. So, how in the world do we figure out when and where this chase ends?
This is the aha moment. This is the simple, beautiful idea that cracks the whole thing wide open. For the cheetah to catch the gazelle, they have to be in the exact same spot at the exact same time. That means their final position, x, and the time it took to get there, t, have to be the same for both of them. That's the key that connects their two separate stories.
So what we do is we write out our position finder equation for the cheetah, and then we write another one for the gazelle. And since we know their final positions have to be the same, we can literally just set those two equations equal to each other. And when you solve it, you find out it takes the cheetah exactly 5 seconds. In that time, they both travel 50 meters, and the chase is over.
And that really is the whole point, isn't it? I mean, think about it. From the high-tech power of a dragster to the pure biology of a cheetah on the hunt, these same 3 simple equations give us this incredible power to describe, to predict, and to understand the motion that's happening all around us.
So we've gotten really good with this toolbox for constant acceleration. But that just brings up a new, really interesting question. What happens when acceleration isn't constant? You know, like a car shifting gears or a rocket burning through its fuel stages. That, my friends, opens up a whole other level of physics, and it is a fantastic question to dig into next.